Welcome everybody to the 8th session. Thank you very much for coming. I'd like to introduce Michael Hoofknuffel. Today he's going to be speaking to us about when products commute with quotients. Thank you.
Roy, can I just speak anywhere or must I speak towards the microphone?
I think anywhere works.
It's fine.
This is the one that's picking you up.
Okay, well, thank you to everybody joining us online, and thanks everyone for coming. So what I want to speak about today is really about this formula here on the screen, a very intuitive formula. And this is got to do with when products commute with quotients. So given integers, x, y, a, and b, if you divide x with a and multiply that with y divided by b, we get x times y divided by a times b. Very simple interpretation of the formula. But this basic commutativity of products with quotients it's present really in many different ways, in many different scenarios. So for instance, in the category of groups, if we were given two normal subgroups, n a normal subgroup of G and n prime a normal subgroup of G prime, then the product of the two normal subgroups is normal in the product of the large groups, and there's this canonical isomorphism between the quotient of the product and the product of the quotients. And this isomorphism is guaranteed by the first isomorphism theorem, where the product of the quotient maps has n cross n prime as its kernel. And this basic isomorphism exists in other categories. For instance, in the category of rings, we have a very similar isomorphism. So given ideals, I of a ring R and J of a ring S, there's this canonical isomorphism, really the same isomorphism and for really the same reasons. And again, also in category of R modules, we can quotient by submodules, and for the same reasons, there's this same isomorphism. And so in these scenarios, we have this commutativity of products with quotients, and I'm going to mention many more examples in the talk. But the question is, why is it there, and does it have any consequences? So that's the question I'd like to answer in this talk. But first, we need to formulate the property more precisely. So what do we mean by quotients? And what do we mean for products that commute with quotients exactly? So in each of those categories which I just mentioned, these are all pointed categories. And just to remind you, a pointed category is simply a category which has a zero object, which is an object which is both initial and terminal. And the presence of a zero object gives us a distinguished class of morphisms in the category. And these are the zero morphisms. So between any two objects, there is a zero morphism. It's a unique morphism which factors through a zero object. And for instance, in the category of groups, if X was a group and Y was a group, the zero morphism from X to Y just maps every element in the group to the identity in that group. Now, why pointedness? Because pointedness is a categorical context where we have an intrinsic notion of kernel. What is the corresponding categorical notion for normal subgroup? Well, in a pointed category, we have this notion of kernel. And what is it? Well, the kernel of a morphism F is just an equalizer. It's part of an equalizer diagram where we have the zero morphism here from X to Y. The dual notion is co-kernel. And so if X was a subgroup, a normal subgroup of Y, then the co-kernel of F would be the quotient of Y by that normal subgroup. Okay. Now, to remind you, if you take the product of two kernels, so for instance, earlier we saw the product of two normal subgroups is normal. Well, this is just a categorical fact. It's that the product of two kernel diagrams is a kernel diagram. And much more generally, in any category, limits always commute with limits, provided the category admits the two kinds of limits. So the interesting part of the condition is really about what is happening with co-kernels. And so just to talk a bit about co-kernels, so if F is a co-kernel, so it is the co-kernel of some map, and N is its kernel, then you can think of the quotient of X by the kernel as X quotient N, where N is the kernel. And then if F is a co-kernel, we have this canonical isomorphism. So co-kernel is always the co-kernel of its kernel. And that allows us to interpret this formula here in a pointed category simply as the condition that co-kernels are stable under binary products. And so that's how we'll interpret the formula exactly. So what do I mean by that? I mean that if at the pointed category, we have a pointed category which has binary products, and we ask it to satisfy this condition that given any two co-kernel diagrams, so the Q1 here is the co-kernel of N1 and Q2 the co-kernel of N2, when you take the pointwise product, this is again going to be a co-kernel diagram. So that's really the condition. And so the isomorphisms that we saw earlier are really coming out from this condition. Okay. So what are examples of categories which satisfy the condition? Well, I've already mentioned groups, rings, and modules, categories of modules, but also categories such as monoids or magmas, and even Boolean algebras, hating semi-lattices, implication algebras, and even pointed lattices. It's a very, very common property. And also, there are other non-algebraic examples. So, for instance, dual of the category of pointed sets, pointed topological spaces, pointed ordered sets, and really many more. It's a very, very common property. So that really begs the question, can anything be said generally about these categories? Is there anything more that we can say other than listing examples of categories satisfying the condition? Or what about a category which doesn't satisfy the condition? So here is just a quick example. So we're living inside the category of graphs at the base point or just pointed sets. And we have these two co-kernel diagrams. This co-kernel here, all it does is squash the x to 0. And this co-kernel here is doing nothing. So the co-kernel of the 0 map is the identity map. And when we take the two products, we get this diagram here. So the square just comes from the product of the two codomains here. This is not a co-kernel because if this was a co-kernel, it would be the co-kernel of its kernel. And we know what the kernel of this map should be. It's here. It's the product of these two kernels. And so the effect of this co-kernel would be just to squash x0 to the origin, which is what this is here. And so this just shows you why this category does not satisfy the condition that binary products commute with co-kernels. Okay. So we began with this example of pointed categories and co-kernels. So our notion of quotient was co-kernel. And this was kind of the general notion of quotient behind each of our examples. Of course, not all quotients are co-kernels. For instance, in the category of commutative rings with unity, we don't have a zero object, so we don't have co-kernels. And of course, we have a notion of quotient by congruence, and in the category of sets, for example, quotient by equivalence relation. All these notions of quotients are not examples of co-kernels, but they are examples of co-equalizers. And we also have commutativity of various co-equalizers in other kinds of categories. So for instance, in the category of sets, well-known condition that reflexive co-equalizers commute with finite products in set, in any variety actually. And even split co-equalizers, another kind of co-equalizer, commute with finite products in every category with finite products. And what's even more is that in each of the examples which I've mentioned, where we have the commutativity of co-kernels and finite products, what's responsible for that is actually that, in fact, all co-equalizers commute with co-kernels, at least in all of those examples. So seemingly the most natural condition is that what we're looking at is just that products commute with co-equalizers. And so that's how I wanted to justify the focus on co-equalizers instead of co-products. All right, so from here on out, what we're interested in is just simply a category in which finite products commute with co-equalizers. And just to say again, what does this mean? This means given any two co-equalizer diagrams, when you take their pointwise product, you can have another co-equalizer diagram. So where does this condition live? So I have a picture for you, and listed here are some familiar limits and co-limits. And so what we want to look at is the interaction of these, all possible interactions between them. So I'll draw an edge where a given limit commutes with a given limit or co-limit, and list the kinds of categories which satisfy the condition. So for instance, between finite products and equalizers, of course we have all finitely complete categories. Because if a category admits all finite products and equalizers, it has all limits, and of course all finite products commute with equalizers. And duly, we have all finitely co-complete categories on the other end. So the interesting conditions really come out from looking at when limits will commute with co-limits. The first one is when finite products commute with co-products. And these turn out to be exactly the linear categories. If the category admits finite products and finite co-products, and they commute, the category is necessarily linear, and all linear categories have this property. Another distinguished class of categories is between equalizers and co-equalizers. So if the category admits equalizers and co-equalizers, and they commute, it actually is forced to be a pre-order. And so this kind of fills the edges of the square. And so what we're left with is diagonals. And that's the conditions we're interested in. And I'll just point out that they're dual to each other, so we only really need to study one. Okay. So what are examples of the full condition? Well, any linear category, as I just mentioned, and then all of the categories which I've mentioned before: groups, rings, R modules, lattices, monoids, magnets, implication algebras, hating algebras, hating semilattices, and really many more. Many of the classical categories, algebraic categories, satisfy the condition. Some categorical examples. The weakest categorical example which one can find that I found is the notion of a weakly uniform category. So there is a notion of uniform category due to Dominic Bourne. And every regular uniform category, or even a weakly uniform category, has the finite products of commute with co-equalizers. Example of a uniform category is just the category of monoids, for example. In universal algebra, one of the varieties which have a lot of, there's been a lot of attention on them because they provide a suitably general environment to develop many aspects of commutator theory, abstract commutator theory, is the congruence modular varieties. And it turned out that every congruence modular variety finite products commute with co-equalizers. But then we also have these non-algebraic examples, the dual of the category of sets, topological spaces, ordered sets, and so on. And more generally, any coextensive category with co-equalizers is a category where finite products commute with co-equalizers. And then some more categorical examples. Factor commutable category was introduced by Marie Legrand as a generalization of factor commutable varieties. And these are actually much more general than congruence modular varieties, and they also satisfy the condition. Okay, so what I just want to talk about first is what about the infinite condition? So we're going to look at the finite condition, which we know we actually really only need to look at binary products. So the binary product of two co-equalizer diagrams being a co-equalizer diagram. But what about the infinite condition? So is it true that if a category has that finite products commute with co-equalizers, then so do infinite products? And the answer to the question is not. And so just to give you a quick counterexample, we look at the category of commutative monoids, which is linear, and so finite products commute with co-equalizers. And what we do is consider this relation Cn, which is defined here. So the set of all ordered pairs of natural numbers such that the distance between A and B is less than the minimum of A and B, and A and B is bigger than N, and we take the union with the diagonal. And what we're left with is a submonoid of n squares, and also not only just a submonoid, but a reflexive and symmetric submonoid. Now, it's significant because to generate the congruence from this relation is simply to take the transitive closure here. So I'll just mention it. And importantly, this specific submonoid is part of a co-equalizer diagram, namely this one, where the two arrows here are just the projections. And these are the co-equalizers. Sorry, this morphism here is just taking the minimum n with n, of x with n, for instance. Now, if the product of these co-equalizer diagrams was a co-equalizer, we could say some things. Firstly, this parallel pair determines a relation on the product here. And it's a relation between sequences, an and bn. And what this relation does is just given here. So for all n, an is related to cn. And C is also going to be reflexive and symmetric just because each of the CNs were. And so again, the congruence it generates will just be the transitive closure of C. And that's just to say that the kernel congruence here of M is the transitive closure of C, if this was a code. Now, why focus on this infinite product? Well, because we can form these two sequences here. Just take sequence n for all n greater than 1, and then this 2n, n times 2n plus 1 for n greater than 1. And then the point is that m equalizes these sequences, because what does m do pointwise for each n? Well, it takes the minimum for each x, let's say, it takes the minimum of x and n. So since this is bigger than n, it will just be n. Okay, now if that diagram is a co-equalizer, so if this diagram here is a co-equalizer, then the kernel congruence of M is the transitive closure of C. And so those two sequences would give us a sequence of sequences such that the beginning sequence is N and the last sequence is the other sequence, where each consecutive sequence is related by a C. And what we can do is look at the kth components of each of these sequences, which would have to be related by these relations CK, which I described earlier. And the CK was such that the way it was defined was such that the difference between AK and AK1 here is it's going to force a bound, and that bound is going to be given here. So just to say this again, this AKI related to AKI plus 1 being in here will force this to be true. And then inductively, we can just get that AK to the K is less than AK0 times 2 to the K. And so that forces this contradiction, so that we actually don't have this commutativity of infinite products with general co-equalizers. Okay, so the first thing to do is to describe the varieties of algebras where the condition is satisfied. And the characterization, the varietal characterization is the conjunction of two conditions. The first condition is something I'm going to describe now. So just some terminology. Given any diagram of this form, we say that it admits a common co-equalizer if there is a morphism Q out of X, which is simultaneously a co-equalizer of both of these parallel pairs. Then we say that binary products preserve common co-equalizers if given any two such diagrams, when we take their point, two such diagrams which admit a common co-equalizer, their pointwise product again admits a common co-equalizer. So this condition already has some consequences for varieties. So if we, and namely it forces the variety to have constants. And just to show you how, suppose we had a variety which didn't have any constants. That would mean that empty set is initial, And so if X is any non-empty algebra, we can then form these two diagrams here and here. Each of these have a common co-equalizer, the terminal arrow on the left here and the density on the right. And so if we took the pointwise product, we get this diagram, and this has a common co-equalizer. It's just if it has a common co-equalizer, of course the co-equalizer here, which is the first product projection, to be the co-equalizer here, which is the identity. So in other words, it would force the first product projection of this product X with X to be an isomorphism. And that can only happen if X has at most one element. Right, so if V is a variety which has non-trivial algebras, it needs to have constants. Okay, so for instance, in the category of sets, binary products don't preserve common co-equalizers. But already in the category of pointed sets, they do. And in fact, the general theorem behind this is just that, in fact, in every pointed category with finite products and co-equalizers, products will preserve common co-equalizers. Okay, so then just to talk about this universal algebraic description. So the characterization is that a variety of universal algebras has that finite products commute with co-equalizers, if and only if its binary products preserve co-equalizers, and then a certain Maltsev condition, certain equational condition holds. This idea of the equational condition is a bit ugly, but here it is. So it's just saying that V admits binary terms and unary terms, and then much larger terms which satisfy these equations. And that's it. So at least for pointed varieties, we know that the condition is it's an equationally definable condition. Right. So for pointed varieties, the condition can be equationally described. And what I want to talk about now is how this relates to Green's shifting lemma. So this is one of the celebrated results in universal algebra says that a variety of universal algebras is congruence modular if and only if it satisfies the shifting lemma. The shifting lemma simply says that for any algebra X in our variety and any congruences R, S, and T on any algebra, or on the algebra, if R meet S is less than T, then this diagrammatic condition here holds. So given any relations which are, any set of relations involving the solid lines, you can induce the relation by the dotted line. So I've already mentioned, this is, so varieties which satisfy this condition are precisely the congruence modular varieties. Okay. So I already mentioned this. Right, so how does this connect up to the condition? Well, given any category, we can associate to that category the category of split epimorphism, category of points. And there's a codomain assigning functor, and then the fibers above any object of that functor is called the category of points of a specific object. So the fiber above X with respect to this functor is just the category of points. You don't really need to know what it is, but just for the purposes of this talk, we can just think of it as a very general concept where to every object in the category, you can associate a pointed category. And one of the celebrated results in categorical algebra is that a finitely complete category is a Maltsev category. It's the categorical notion associated to Maltsev varieties, if and only if every fiber of C is uniform. And that's a theorem of Dominic Born in 1976. And this theorem opens up this line of questioning. What conditions on a category can be localized in this way? And what kind of properties can be obtained by such a localization? It turns out that our property has a relationship to the shifting lemma in the following way. So given any pullback square, we can, let's say in a variety, we can restrict the shifting lemma to the case when the R here and the S are specific congruences, namely the kernel pair congruences of complementary pullback projections. So given a pullback square, let R be the kernel pair of the P1 here and S be the kernel pair of the P2. And then you ask that the pullback, that with respect to these congruences, the shifting lemma holds, which is just to say this condition here. And so let's say that that's the shifting lemma on pullbacks. And what it turns out is that for a variety, finite products will commute with co-equalizers in every category of points, if and only if the shifting lemma holds on pullbacks in the variety. And so this draws this connection between the shifting lemma and this condition. And it also opens up a line of questioning, which is how much of the theory of congruence modular varieties actually generalizes to varieties in which the shifting lemma on pullbacks holds. Because after all, the shifting lemma characterizes the congruence modular varieties. And so that's one kind of question which I'm going to get to in the second half of the talk. Okay, so we're not just going to go back to simply a pointed category in which finite products commute with co-equalizers. And these categories turn out to be related, or at least I asked this question at the beginning of the talk. What can be said of these categories? And what can be said is a lot about how topics involving centrality behave in such categories. So I'm just going to describe centrality as how it's formulated in the subgroup. So we say that two morphisms, F from A to C and G from B to C in a pointed category, commute if there exists a morphism here making the entire diagram commute as a categorical diagram. Then the main intuition behind this is that, for instance, in the category of groups, two subgroups will commute if and only if they commute really in the group theoretic sense, which is just to say that AB is BA for all A and A and B and B. Then we say that a morphism is central if it commutes with the identity on its codomain, which is just what this diagram is saying. And in the category of monoids or groups, a morphism is central if and only if its image is lies in the center of that, in the center of its codomain. Then lastly, an object is commutative if the identity is a central morphism. And so we can talk about the full subcategory of commutative objects and just give it this symbol here. So two subgroups commute in the categorical sense, if and only if they commute in the group theoretic sense. Morphism is central if and only if its image is a central subgroup in the group theoretic sense. And an object is commutative if and only if it is in the Boolean group in the group theoretic sense. Okay, now in the category of monoids and groups, we can, so in the category of monoids and groups, we can form all central morphisms from one group to another or one monoid to another. And this forms a commutative monoid, and this monoid acts on the Hom sets with just as it's given here. And this structure here is part of what is called the additive core inside the unital category, which has been established in this paper here in 2002. And one can wonder, what is the most abstract setting in which one can have this additive core? So for instance, in this paper, it establishes this additive core for unital categories, but this additive core is also present for weak unital categories, which are different. So just to remind you, a category is said to be unital if the product inclusions here are always jointly strongly epimorphic, and it is weakly unital if they're simply epimorphic, jointly epimorphic. And then one of the main things that I just said is that abstractly one can have this additive core, which I've just described in any weakly unital category. So there's the notion of central morphism, the central morphisms from one object to another always form a commutative monoid, and this acts canonically on the Hom sets in any weakly. There's also some other behavior of central morphisms in weak unital categories. So we have this canonical commutative monoid action, but also the full subcategory of commutative objects. It's a linear category. It's closed under finite limits. It's closed under regular quotients in C. And then some other properties. For instance, if F is a central morphism here and Q is any regular epimorphism out of the codomain of F, then this composite is going to be central. Another property here is that if you're given any two regular epimorphisms into the same object, and those two regular epimorphisms commute, then in fact the object X is commutative. So there's some behavior of central morphisms, and all of this behavior exists within a weak unital category. So now going back to the commutativity of finite products with co-equalizers. I want to just visualize a certain property as a variation of the shifting lemma, which I mentioned earlier. And that property is just given here by star. So whenever you have, so given any morphism f from x cross y into z, if f of x0 is equal to f x prime 0, then you can add a y and the equality still holds. Now, as it turns out, a pointed category with co-equalizers, which satisfies this condition, has that finite products commute with co-equalizers and vice versa. So one can characterize the commutativity of finite products and co-equalizers just by this very simple condition. Okay, and this condition is really closely, intimately connected to this behavior that I mentioned of central morphisms. So the first thing is that between any central morphism and any other morphism, there's a unique cooperator. So in a category satisfying this very condition, there is always a unique cooperator between any central morphism and any other morphism. In other words, there's a unique way to add things. Now, in the context of simply a category satisfying this condition, a pointed category satisfying this condition, which has finite limits, we have, again, this commutative monoid action. And moreover, the full subcategory of commutative objects, it's linear, it's closed under finite limits and regular quotients. And much of this behavior, which I've already mentioned, which is true of unital categories and weak unital categories, is still present in this more general context. So what I've just remarked is that nearly all properties that you could mention about central morphisms generalize to this context, at least that I found, generalize to this context of simply a category satisfying this condition. Okay, so just one quick remark, and that is that these two notions are separate. So the category of lattices has a specific condition which allows every category of points to satisfy the condition which I've already mentioned. It's called the majority category, and that condition just implies that every category of points is centralic. It satisfies the condition which I've already mentioned. And so this shows you that the condition is separate, because if this condition was the same as being weakly unital, then every category of points here would be weakly unital. But that's not true, because as shown by Nelson Martins Ferreira, a variety of lattices is distributed if and only if it is weakly nullative, and only if every category of points is weakly unital. Okay, so examples of categories satisfying the condition. Of course, as I've mentioned, any category in which, every pointed category in which finite products commute with co-equalizers, it's the main example. But finite, what about categories just satisfying this condition, which without the commutativity of finite products with co-equalizers? Well, we have every unital or every weak unital category as an example. So every pointed Gun category in the sense of Dominic Braun and Marina Brown, every normal category in the sense of Zurab Janalitsa, and again, we pointed back to commutable category. And so there are many categorical examples of this condition. So one thing I haven't mentioned is, for instance, in the category of monoids or groups, the full subcategory of abelian groups sits inside of the category of groups, and there is an abelianization reflection. And also in the category of monoids, this reflection here exists for the category of commutative monoids sitting inside of monoids. So what is abstractly responsible for this reflection? And how can we produce it in our context? Well, it can be produced in any weak unital category, so any unital category, regular unital category with co-equalizers. You can produce this reflection. But in a weak unital category, this is no longer necessarily the case. And it turns out you can strengthen this concept of centrality category, which I forgot to actually define, and I do apologize, but it's really just the category satisfying this functional condition I mentioned. You can strengthen it to the point where it's still less than a weak unital category, and you can still produce this reflection in this category, in this context. And examples will include more than just unital. They'll also include pointed factor commutable categories. So this provides unification between this, where this reflection exists in the unital context and also the factor commutable context. Okay, one thing I wanted to mention is that there is one of the important properties relating to unique factorization under direct product is so-called strict refinement property in universal algebra. So this essentially says that products can decompose uniquely into irreducibles, just like the fundamental theorem of arithmetic for algebras. And one theorem there is that, for instance, in groups, centerless groups have the strict refinement properties. You can always factor a centerless group into centerless irreducibles in a unique way. And this is still true of monoids. And in fact, it's still true in the context of a category satisfying this centrality condition which I've mentioned. Okay, so just to summarize what's happened, the commutativity of finite products with co-equalizers is a very common condition in algebraic conditions, algebraic categories. It's intimately connected to the topic of centrality, which itself is intimately connected to many other topics. Many notions in group theory depend on commutator existing, definitions like nilpotence, for instance. And so all of these topics are intimately connected. Another thing to say is that, for example, centrality, as I've mentioned, is really connected to this topic of unique factorization in a specific way, and that carries over in the categorical context, even in this very weak context which I've mentioned. Another interesting condition which I've tried to research but I haven't found much is, what other limit co-limit conditions hold, are there, and what are their relationships. So further plans that I have with this work is to clarify this topic of centrality, not of morphisms, but of equivalence relations. So one of the categorical ways of dealing with abstract commutator theory is through centrality of equivalence relations, notion of connector, and it's developed in, parts of it is developed in the context of what's called the Boom category, and it's developed in this paper here. Sorry, this paper here. And so what I would like to do is to explore that further here as well. Okay, so thank you for listening, and here are my references. Roy?
Are there any questions?
I don't know if anybody online is speaking. Okay, no questions, I guess.
Okay. Thank you very much.
Okay. Thank you.
Then I guess next week we don't have anything planned yet. If anybody wants to do a formal session, but please say that. Otherwise, we can maybe talk workshops next week. If anybody's willing to get
Too early for the posterity one. And then like the week.
We can also take another break next week.
Yeah, I guess you also spoke about these more informal things. Just talk about some ideas.
Yeah.
Let's do that.
Okay. Yeah. We can have our first informal one. Maybe if you want to have like and you can see by Wednesday, Thursday, and we can sort of come
I don't know if the people online can hear you, right?
hello. Can the guys online hear me?
We can't hear.
Now we hear you, but we couldn't understand what you were saying before.
Sorry. Okay. So next week we don't have anything planned formally as of yet. So unless somebody wants to speak next week, we think maybe we can have like an informal session where we sort of have a discussion about some topics that we haven't necessarily explored fully yet. So we can try that for the first time next week.
But we might not do that with the next one.
We'll be at CT next week in Santiago.
Ah, right.
So
Oh,
we
that's
will
also.
not join you.
Okay. All right. Oh. There's no sense next week.
Well, I mean,
We are going.
yeah. But I mean, we wouldn't. I mean, we are saying informal things that might just be locally. So maybe that actually maybe that works well, right? Because if the online people are potentially going to be going to a conference, then the local people could meet up or something.
Right.
Anyway, either way.
Okay. I mean, I think it makes sense to maybe not like record.
Yeah. Yeah.
A lot of sessions. But, maybe
Well, I don't know. But also, there's probably going to be not have slides and be on a board. And
right.
stuff
So
like
we
that.
don't have the tech for that. Okay. Okay. Cool.
So the point is, for the purposes of the online people, it won't be happening next week.
Yeah, sure.
Unless we send out an email, I guess.
Right. Yeah.
Okay, thank you, Elena, and thank you, Luca, for
Thank
joining.
you. Thank you. Bye.
Bye-bye.
Bye.
Bye.